All right, let's talk about series. So, depending on your pre-cal experience, and by pre-cal experience, I mean all the courses leading up to pre-cal, you may have worked with series quite a bit, maybe just a little bit, or maybe not at all. So I'm just going to proceed as if you've never seen this before, aside from me using that first symbol, that capital sigma, to say I'm adding up a bunch of, small areas to get a total amount of area that becomes an integral. That's a theme in this class. So I'm going to start there and say that this just means like a sum. Very nice. Okay. AN is the numbers we're adding. And I'll show you what I mean here in a second. Sn is, less common in this course, but this kind of represents the total after adding n terms. And n is the index. And n is a number that it kind of just like marches forward by one each time. Oftentimes it starts at one and it's one, two, three, four, up to some point or all the way up towards infinity. But it doesn't have to start at one. And that's the index is what makes computer science students think that these series feel a lot like for loops. And I took very little computer science in my educational experience, but I took enough to remember that I understand how they're similar. And rather than try to describe to you in general about this notation, like where all the pieces go and what they do, I think I'd rather just like kind of work a couple of examples around it, let you toy with it a little bit, and let you discover it that way, because I think that's going to be a more lasting technique. Also, it's going to seem really familiar from our treatment of integrals. Okay, so we're going to rewrite each series as a sum. Okay, I'm going to do one of them for you. Okay, we're going to sum as n runs from 1 up to 6 on 50 minus n. Okay, so that's what we're going to do. 50 minus n. N is 1. That's 50 minus 1 is 49. Plus, because we're adding, 50 minus 2. Okay, and 50 minus 3, 50 minus 4, 50 minus 5, and 50 minus 6. So 1, 2, 3, 4, 5, 6. There's 6 terms. That makes a lot of sense. Okay, that's how we do that. You should try this with the other two and check your work against mine because this is a skill you need to have. Okay, so write in your answer with the video pause. Make sure you know what you're doing and check your work against what's going to appear on the screen in about 5 seconds. There you go. Okay, not too difficult, just follow the pattern within, there's not a whole lot to say about it. Okay, rewriting the sum using sigma notation is a little trickier, like going backwards. And that's that modeling skill that we just don't do a great job of building in K-12 math, at least in this area. We do a really good job with algebra and with some other stuff, but not so good with the, writing an equation to model a scenario. It's tough. It's a hard problem. But these are easy enough. 1, 4, 9, 16, 25. These are square numbers, okay? So that means that the things that we're adding together, and since we're adding them together, it's going to be a sum. And it's going to start with n equals some number and going up to some other number. But I think it's good, especially when you start, to just like kind of write down the rule as you see it. It's n squared. Okay, and so it looks like n is starting at 1 and ending at 5. Okay, and so it's like 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Makes sense. Okay, and that's how you write it using sigma notation. Okay, I might do one more. Right next to it. 4, 8, 12, 16. Okay, so this is counting by 4. So this is 4 times n. 4 times 1, 4 times 2, 4 times 3, 4 times 4. So we're adding 4n and starting at 1 and going up to 4. But what I would say is, like the first one, you could have written that as n plus 1 squared, like with parentheses around the n plus 1, as n ran from 0 to 4. There's going to be a variety of ways that you can write a given series. Okay, but they're all equivalent. Okay, so now you work these with the video paused, and I'm going to just bring in my answers here in just a few seconds. All right, there you go. So hopefully those aren't too surprising. Maybe you're looking at the very last one, and have a different expression from what I wrote. That would make a lot of sense. I kind of intentionally did that one a little different. But just to point out that if you had written the sum from 1 to 4 of n over n plus 1, that would be the exact same thing. It would be just as good. Okay, so there's this other thing that also you may have some experience with and you may have absolutely no experience with called factorial. It's something that comes up in probability and statistics and really all over the place. Also in calculus because of this thing that you'll see with the pattern of taking successive derivatives of polynomials. Okay, n factorial is where we multiply, when n's like a whole number, a whole positive number, we multiply n times n minus 1 times all of the positive numbers below it until we get down to 1. So for example, like 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. And what can frequently happen in math problems is we need to divide one factorial by another, and they cancel off really nicely, oftentimes. Okay, so if we need the value of 8 factorial divided by 10 factorial, that's where I'm going to, kind of write out 8 factorial is 8 times 7 times 6 times 5 times, times 2 and 1. And 10 factorial has, almost all of the same numbers. It has 8 through 1. So I'm going to say that's 10 times 9 times 8 factorial. And then I can cancel these off like that. And then I will be left with a 1 in the numerator and a 90 in the denominator. I told you earlier about capital S sub n, like the nth partial sum, and we can do one of those. That's not the biggest deal in AP Calculus, but the concept of it is kind of important. Okay, so if S is the sum from 1 to infinity, which is going to be the type of sum we're going to be very interested in this class, of n factorial divided by 2, find S sub 5. Okay, well, let's say, just write out the terms. So let's say S equals, start with 1 factorial is 1 over 2, plus 2 factorial is 2 times 1 over 2. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And we're going up to infinity, but we need S5, so we're going to need up to the 5th term. Zoom out also. Divided by 2. Okay, now we're going to cancel off a bunch of 2's. And we would have, that's going to be a half plus 1 plus 3 and 12 and 20 times 3 is 60. All right, so 72, 75, 76 and a half. Okay. Now you should try to find S6 on your own for that sum over there. You should do that with video pause because the answers are going to come in just a few seconds here. All right, there you go. So S is, you write out the terms, and one thing I kind of neglected to do, which is, it's a big deal, is I didn't put the dot 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 over there for S, because S is the infinite series, and S5 is the finite sum. Okay, and so I made sure to do that over here, but S, continues going on forever, but S6 just only has 6 terms in it, right? And it had this interesting pattern where we kept really, the closer we looked, we were just adding -1 over and over again. Okay, so it looks like the more terms we add, the more negative our total gets, and that's going to be the type of pattern we're going to be interested in this class. Okay, classifying series, that's the last thing I got for you. Okay, I just figured today would be a good day to build a couple of skills that before we even start in on the series. And a P series is where n is a power in the denominator. That's really it. N is taken to a power in the denominator, like 1 over n squared, 1 over the cube root of n, 1 over n. These are all P series. And a geometric series kind of looks like an exponential function. Okay, it's going to be some number times some ratio to the nth power. Okay, we're going to see n as the exponent in a geometric series. All right, so write the sum and sigma notation and determine if it's a p-series or geometric series. So, okay. Okay, 8, 12, 18, 27. Okay, that's going to be an exponential pattern. Okay, because we start at 8 and each time we multiply by 1.5. All right, so that's 8 plus, in fact, I'm going to even write it in. 8 times 1.5 plus, okay, 12 times 1.5 is 18, so that's 12. Multiply it by 1.5 a second time, that's 18, and I think that's enough to see the pattern. I'm going to write that as the sum as n runs from something up to infinity of 8 times the ratio is 1.5 to the n. But the question is, where do we start? I'm thinking about, okay, the first one is 8, and there's no 1.5s. That's why we're going to start the sum at n equals 0. And now you could have said 1.5 to the n minus 1, and then n would have started at 1, but it'd be the same thing. Okay, it doesn't really matter. Okay, 1, 16, 81, 256, and so on. Okay, that's going to be 2 to the 4th, 3 to the 4th, 4 to the 4th. These are the fourth powers. Okay, so 1 to the 4th plus 2 to the 4th. Okay, so I guess it's kind of a p-series. Oh yeah, I definitely had a point to make on these. All right, so that's where we're going to start, where n equals 1 and goes up to infinity on n to the 4th. And now, really, to make it a p-series, maybe we would call that 1 over n to the negative 4. But this is really not the type of series we'd be very interested in, as, you know, adding up all of the terms as, you know, an infinite number of terms which are getting larger and larger, that total would clearly go to infinity. And you can say the same thing about series on the left. So 1 over n to the negative 4, that is a p-series, but not really the type we would be interested in this class. We're going to be interested in a p-series where p is positive. Okay, and then this one was geometric. All right, now the last one's kind of got, it's alternating. So, you know, and it's going to be like that one up above that had the negative 1 to the n plus 1. I didn't talk about that a whole lot because we'll study that in depth in this class. But 48 minus 36 plus 27 minus something dot 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 following the same pattern. Well, the pattern is we're multiplying by 3/4. So I'm just going to say, you know, there you go. It's sum from n equals 0 to infinity of 48 times negative 3/4 to the n. Because n is the exponent, that makes it a geometric series. That's all I got for this video. Thanks for watching.